Hi, welcome back. My cat has decided to, oh, she just got off. She was doing her treadmill. I was hoping you guys could see that. Maybe she'll hop back on, but probably not. All right, so welcome to the mini lesson on the parasympathetic division. So we just got done covering the sympathetic division of the autonomic nervous system. That's our fight or flight or freeze or exercise control of what's going on with our visceral effectors of the smooth muscle, cardiac muscle, and glands. So next we're going to take a look at the parasympathetic division, and then I'm going to tag on dual innervation to the end of this one because parasympathetic division is not quite as complex as sympathetic, so it's not going to take that much time. But one thing I did want to mention as I was looking at my notes, I forgot to mention when we were talking about sympathetic receptors, there's a little blurb at the end of the notes before it jumps into parasympathetic talking about a few locations where the postganglionic neurons release not epinephrine or norepinephrine, but acetylcholine or nitric oxide, the NO. So it looks like the word no, but it stands for nitric oxide. So at the postganglionic neurons of the sympathetic division that innervate the sweat glands of your skin and the smooth muscle and the blood vessels of your skeletal muscle and brain, it's listed there in the book and in the notes. So I know it's a lot of information. Those two places, that postganglionic neuron is going to release acetylcholine. So sweat glands and blood vessels in your skeletal muscles and brain. And then the release of nitric oxide is the smooth muscles of blood vessels to your skeletal muscle and brain. Not the skeletal muscles and brain, but the smooth muscle around the blood vessels. The smooth muscle is our effector. So it's in this section, the very bottom section of the notes here, it says sympathetic release of ACH and NO. So that goes along with the sympathetic division, but I wanted to make that a part of what I talked about before we move on into the parasympathetic division, which is where we're heading to next. So we have this diagram here. Helps us to, is very similar to the sympathetic division. So it's showing us the distribution of the innervation. So where does the preganglionic neuron start and where does the postganglionic neuron start and where is the innervation? Where is the target tissue? Now, if you remember, we had the lateral gray horns in the thoracolumbar or the thoracic and lumbar segments of the spinal cord, T1 to L2. Kind of in this area right here, this was sympathetic, right? Now, parasympathetic is not there. Those preganglionic neurons, the lateral gray horns, that's all dealing with sympathetic control. Where are the preganglionic neurons in the parasympathetic division? They are located in the brainstem and the sacral segment of the spinal cord. So while the sympathetic division can sometimes be called the thoracolumbar division of the ANS, the parasympathetic can sometimes be called the craniosacral division of the ANS because the preganglionic neurons originate in the cranium, not the cranium, the brainstem, which in itself is in the cranium, the brainstem and the sacral segment of the spinal cord. Now, as far as ganglia, there's just 4 that are listed here. So if you remember, again, just to compare, sympathetic had the chain ganglia, the collateral ganglia, and the adrenal medulla. Here we have 4 ganglia that are mainly associated with your cranial nerves. And then the rest of them are what we call terminal ganglia. Terminal ganglia means that the collection of those postganglionic cell bodies are at the very end of the preganglionic pathway embedded in the wall of the organ. So if we try to find those, I have a cat on my lap. Here's one. Okay. So if we look at where the red finds the black, right? The red is a preganglionic, the black is a postganglionic. We can see those located in the organ. So I'm circling all of these in green. So that's our terminal ganglia. Sometimes they're called intramural because they're kind of in the walls, I guess, of stuff. Nope, the top 2, those are actually in the ganglia. Okay, so those terminal ganglia, we don't have a really obvious, blob or, swollen area that resembles a ganglia like the sympathetic chain or the collateral. It's really embedded in the wall of the organ, so you really can't see them unless you go and do a specific dissection. So those are the locations of where the pre and the post meet, with the exception of these 4 ganglia that are associated with the cranial nerves. And those are our pterygopalatine, ciliary ganglia, submandibular, and otic ganglia. And if you'll notice, they're associated with your cranial nerve number 3, which is your OOO, ocular motor. Cranial nerve number 7, OOO, to touch and feel, facial. Cranial nerve number 9, OOO, to touch and feel very good, glossopharyngeal. And cranial nerve number 10, which they named for you, so you already know that one, is the vagus. So cranial nerve number 10. But that goes to the terminal ganglia, not these 4 named ganglia. So with that being said, the preganglionic neurons travel towards these 4 ganglia to meet their postganglionic neurons in the nerve pathways of these cranial nerves. So it's not their own, there's not their own parasympathetic nerve, just the nerve fibers travel within the cranial nerves, along with all of the other sensory or motor, depending on the function of the nerve. For the rest of, and that's not very much, so we're only innervating a few things of the face, so like your tear glands, your smooth muscle of the eye, and your salivary glands. Everything else, thoracic cavity, abdominal pelvic cavity, so cardiovascular system, respiratory system, digestive system, urinary system, reproductive system, lymphatic system, all of these organs have their preganglionic information traveling along with the vagus nerve, along with other things that are traveling along with the vagus nerve. Like 75% of all parasympathetic information travels to their destination via the vagus nerve. So it is a pretty busy place. I'm trying to erase all my little squiggles here. Okay. So when we take a look at this, it's not quite as strictly organized as the sympathetic division was. So that's why it doesn't take as long to go through the parasympathetic division. But you'll notice the list of organs, or the pictorial list of organs, is pretty much the same. So we have eyeballs and heart and lungs and liver and stomach and spleen and pancreas and large intestine and small intestine. So we're going to talk about dual innervation later. So whatever we have on this parasympathetic picture, if it's also on that sympathetic picture, that lets you know that both of those organs are receiving sympathetic and parasympathetic information. Okay. So we talked about, so this is, flipping you back to the picture of the little kitty sleeping in its food. So parasympathetic was our rest and digest. It's kind of activating our digestive functions, our urinary functions, kind of our most of the day functions, decreasing blood flow to our skeletal muscle, increasing blood flow to our digestive viscera and to our kidneys, and regulating, keeping your heart rate low when you're not very active, keeping your respiratory rate low when you're not very active, kind of keeping your blood pressure low when you're not very active. So that is your function of the parasympathetic division. So let's take a look at the receptors. And so the receptor names for the parasympathetic division are quite a bit different. So for the sympathetic, we had alpha and betas. So remember, our alpha 1s and beta 1s were excitatory. Alpha 2s and beta 2s were inhibitory. And our beta 3 was just going to the adipose tissue for like lipid release. Well, in the parasympathetic division, our 2 type of receptors are called nicotinic and muscarinic. Okay. Now that's kind of interesting because nicotine is a pretty common word, and most people know that that is the substance found in cigarettes and tobacco. Muscarinic, not quite as common, but muscarin is a chemical that's found in this amanita mushroom, toadstools, I think that's what they're called, and it's a toxin. Both of them are toxins. So why the heck would scientists name receptors in our body after toxins, nicotine and muscarin? The reason why they got those names is because scientists knew that it was acetylcholine was a neurotransmitter. Postganglionic parasympathetic neurons release acetylcholine. Just to compare, postganglionic sympathetic neurons release norepinephrine. Epinephrine from the adrenal medulla. But postganglionic parasympathetic neurons release acetylcholine. But in the process of learning this, researchers, I found that of the what they are calling the nicotinic receptors that naturally respond to acetylcholine, nicotine also binds. So nicotine binds to the nicotinic receptors. Muscarine binds to the muscarinic receptors. That's why they got their names, is because they also found that these naturally occurring chemicals, nicotine and muscarine, mimic acetylcholine enough to bind to those receptors and trigger the response. So that's why, you know, smoking tobacco or chewing tobacco or having products with nicotine in them gives you kind of your physiological reactions, is because nicotine is mimicking acetylcholine, triggering that parasympathetic response. Muscarine, if you consume these mushrooms, would also mimic acetylcholine and trigger those cells' responses, but typically in an exaggerated way because your body is regulated and maintaining homeostasis. But if you put in excess nicotine or excess muscarine, your body is going to react excessively to those. So, for example, some of the side effects of muscarine poisoning are excessive salivation, abdominal cramping, diarrhea, nausea, kind of like digestive issues. And if you think about it, that kind of makes sense, because what is the parasympathetic primary, what's our rhyme, right? Rest and digest. So if you're triggering the digest part of your parasympathetic activation in excess, you're going to be making more saliva. Your smooth muscle around all of your small intestine, large intestine, stomach's going to be contracting a lot more powerfully, causing cramps and diarrhea, maybe vomiting. So we're increasing all of that activity of your muscarine, or your normally what would be acetylcholine, but the muscarine is coming in as a toxin and triggering excessive responses. So that's where the names come from. Hopefully that helps with your understanding. For the response, right? So what's the response of these receptors when acetylcholine binds? Well, nicotinic is always excitatory. Excitatory. Make sure I spell that right. And we've seen nicotinic receptors before. I'll erase muscarinic so I can draw a picture here. So this is the same type of receptor that we saw in skeletal muscle activation, right? So here's our plasma membrane. Acetylcholine comes in, binds, the gate opens, sodium ions flow in, depolarizing the cell. Those neuromuscular junction receptors, the receptors on the cell body and dendrites of our chemically gated channels, those were all nicotinic. We just didn't call them that. We just called them acetylcholine receptors. But that is the type of receptor that they are. Nicotinic, excitatory, and it's excitatory because sodium enters when the chemical binds and you're depolarizing the cell. So that's always going to be excitatory. Now, for muscarinic, I'm not going to draw quite as a similar type of picture because it's different. Muscarinic, and its results vary. Could be positive, or when I say positive and negative, I mean excitatory or inhibitory. And the reason why it varies is because these are G protein receptors. So when acetylcholine binds to a muscarinic, it could be excitatory if that second messenger that shows up in the cell is an excitatory second messenger like cyclic AMP. Or it could be inhibitory if that second messenger that shows up into the cell maybe breaks down cyclic AMP or opens a channel to depolarize the cell. So muscarinic are G protein receptors compared to the chemically gated channels or chemically linked ion channel linked receptors of the nicotinic, which are always excitatory. Muscarinic are G proteins, and they can vary depending on the second messenger that shows up, the enzyme in the second messenger. So we'll see the distribution of where we find the muscarinic receptors and their, excitatory or inhibitory response when we take a look at dual innervation. All right. So I think I covered that. All right. So that wraps up parasympathetic. Like I said, it's not as complex as sympathetic division. It's your rest and digest. It's kind of maintaining most of your day's autonomic function, with a few exceptions of when you have to go into a fight or flight. And on a day that you don't exercise, you may never enter sympathetic activation. You could be in parasympathetic all day and all night until you exercise, or maybe you almost hit a raccoon running out in front of you or something. So unless you are in a crisis mode, parasympathetics just kind of keeping things homeostatic. Okay, so now that we're done covering parasympathetic, let us do a little bit of comparison, because it's always helpful to reinforce what we're learning when we can compare it, the two different ways. So in sympathetic, our ganglia, that interaction between the pre and the post, typically happens close to the central nervous system, with the weird exception of the adrenal medulla. It had a really long preganglionic neuron. But our preganglionic neurons are usually short. Okay, look at our parasympathetic division. It went from the brain stem or the sacral segment of the spinal cord all the way to the organ at those terminal ganglia. So these are long. So your preganglionic neurons are short in the sympathetic division and long in the parasympathetic division. And I'm going to draw some Schwann cells on here. Can't fit as many on the sympathetic. Just to remind you that in both divisions, the preganglionic neuron is myelinated. Okay. All right. So with that long and short, we can go back and say, okay, so on the sympathetic division, because the preganglionic neurons are short, the postganglionic neurons are long, and the postganglionic neurons are short in the parasympathetic division, because that ganglion, remember, is located right in the wall of the organ, so it doesn't have to travel very far. With, again, on the sympathetic side, the weird adrenal medulla, that preganglionic neuron is really long because it goes all the way out to the adrenal gland. Okay. All right. Neurotransmitters. So if we take a look, they have the neurotransmitter acetylcholine is indicated by the black arrow. And if you'll notice, both pre and post ganglionic neurons, both preganglionic neurons in sympathetic and parasympathetic divisions both release acetylcholine. And we just said acetylcholine, when it binds to nicotinic receptors, which are on the postganglionic neurons, is always excitatory. So whenever a preganglionic neuron fires within either division, it will be excitatory on that postsynaptic neuron. Postganglionic neuron. I knew that didn't sound right. So the preganglionic neurons will always be excitatory on the postganglionic neurons in both divisions. So that's the black arrows is representing acetylcholine. For the sympathetic division, we have in the varicosities, so if you remember the varicosities is the synaptic structure of the sympathetic division, it releases norepinephrine at the synapses on your target tissues. If we are taking a look at that weird exception of the adrenal medulla, we have both norepinephrine and epinephrine being released directly into the bloodstream, which will again make its way to the target tissues via the bloodstream. Okay, so sympathetic preganglionic neuron releases acetylcholine, postganglionic neuron releases norepinephrine. Adrenal medulla, those endocrine cells will release epinephrine and norepinephrine into the bloodstream. For the parasympathetic division, the preganglionic neuron releases acetylcholine, and the postganglionic neuron releases acetylcholine. Okay. And then for the receptors, if you remember, we have alpha and beta receptors over here on the sympathetic side, and we have nicotinic and muscarinic receptors over here on the parasympathetic side. Okay, so we just kind of boiled down some of the key features of both of these divisions. Okay. The next thing I'm showing you is kind of talking a little bit more about that dual innervation when you have an organ that has both sympathetic and parasympathetic. So this is a table straight from your textbook, table 16.3. It should, I don't know what edition this table came from, so it might be a little bit different. But you should have a table of the dual innervation of specific organs that have both sympathetic and parasympathetic. So let me take a look. Let's take a look at one example. I'm going to highlight the heart here, because that's a pretty easy one to kind of recall your experiences with your heartbeat, because it's there, it's always there, right? So in sympathetic activation, we talked about sympathetic activation increases heart rate and increases blood pressure, which would be the stronger the heart beats, the more forceful the contraction, the more blood pressure it's going to be. And in parasympathetic division, it's a lower heart rate, weaker contraction, so it's going to be lower blood pressure. So let's take a look at the receptors that are found in the heart muscle tissue itself to respond to the norepinephrine and epinephrine from the bloodstream. Take a look at those guys. Alpha 1s and beta 1s, both excitatory, which is great because that makes sense. We have excitatory receptors responding to the epinephrine and norepinephrine, increasing heart rate, increasing force of contraction, leading to an increase in blood pressure. Now here, all of the parasympathetic receptors that are shown in this table are the muscarinic. So when it says decrease heart rate, force of contraction, blood pressure, that lets us know that these are inhibitory muscarinic receptors. We didn't talk about the cellular mechanisms of why they are inhibitory. We just know that it varies, remember? It could be excitatory, it could be inhibitory because they're G proteins. So for this particular organ, the heart that's dually innervated, you will have an increase with these excitatory receptors with the arrival of epinephrine and norepinephrine in sympathetic activation, and you will have a decrease in the activity of this organ with the arrival of acetylcholine binding to an inhibitory muscarinic receptor. Okay, so that's just one example. You can go through, don't memorize this table, use it more as a reference, or if you have questions about how you're, when you're trying to, if you're just curious or trying to answer a question about which receptors are found at which organ or what the organ is, how it's going to respond based on the neurotransmitter or the division that is active. So I'm going to do one more real quick in the digestive system, right? So sphincters, we have a pyloric sphincter, we have our anal sphincters. So in the sympathetic activation, it reduces the activity of the digestive system. But you might say, hey, but it says constriction. Isn't that alpha 1 is excitatory? Well, yes, it's excitatory, but it's excitatory on what? A sphincter, which is smooth muscle. So you have an excitatory sphincter, it's going to close up, which means food and feces cannot pass through, which in essence is slowing down the activity of your digestive tract. Where in the parasympathetic activation, it's relaxing, it's a dilation of the sphincters, which means the smooth muscles have to relax. So it's going to be an inhibitory muscarinic receptor. But when you relax your sphincters, food and stuff can move through and defecating becomes easier. So make sure that when you're understanding and kind of working through this dual innervation with receptors, you kind of take a step back and say, even though it might be an excitatory receptor, take a look at the tissue, and exciting that tissue might result in an overall decrease in the activity of that organ, which is that digestive system is a good example for that. Okay, all right, moving on. So that was kind of anatomical with the location of the different kinds of receptors. So physiologically, what does dual innervation do? How can we track this? So this is information actually taken from, this is a picture from chapter 21, I believe, that we're going to get to at the end of this term. But it's a really good example of this dual innervation of your sympathetic and parasympathetic. So I'm going to show you first the heart with a little EKG tracing at the top. We can see the top tracing is the rate, do, is kind of slower compared to do. So in the same amount of time, we have more heartbeats. So these would be examples of your maybe parasympathetic activation on the top and sympathetic activation on the bottom, because that's how your heart responds to those two divisions. So let's take a look. I'll get my highlighter back because I'm going to highlight the pathway. So if we're going to take a look at sympathetic activation, which is the orange, so the orange, yeah. So it's going to be these orange, this orange pathway. So here's our preganglionic neuron synapsing into the chain ganglia, right? But it's going to the thoracic cavity, so it's going to leave via a sympathetic nerve, and it goes out, and in this case, it's going to trigger the SA node, which is your pacemaker. So it is getting its information from a higher order neuron, which I'll put it in red here. That comes from your brainstem, in your medulla. Remember, we had our cardiovascular, cardio, and respiratory rhythmicity centers, part of our brain anatomy. So that little red half circle is the inhibitory part, sorry, the excitatory part. So the red, when that is excited, it's going to send this excitatory neuron down to that preganglionic neuron in the lateral gray horn, excited to action potential, boom, preganglionic, boom to postganglionic, boom to the SA node, increasing the heart rate, and then you get a faster heart rate. On the parasympathetic side, so the parasympathetic, remember, comes from the brainstem already. The preganglionic comes to the brainstem, so that's this guy right here. Oops, get back to my highlighter. Yellow. There we go. So preganglionic, it's kind of hard to see because it's yellow on yellow. So it is coming down that nerve, probably the vagus nerve, because we're in the thoracic cavity, and it comes down, and if you'll notice right here, it switches over. Okay, and we'll see that coming into the SA node, and that's going to slow down the heart rate. So that's dual innervation, kind of showing there in the picture of the heart. Now, the other thing that we can see on this slide is I have the word called autonomic tone sitting right over the blood vessels. Your heart also functions, autonomic tone is a background level of activity, just like we had muscle tone. So if you remember the Arnold Schwarzenegger picture with his, bulky versus flabby, the more you work your skeletal muscles, you have a higher background tone. Well, your autonomic function works the same way. So you have a background level of your tone for your heart rate and your blood pressure and your smooth muscles and your blood vessels. So we don't start at either extreme and only can work in one direction. So for example, if we were to just purely have sympathetic activation with no parasympathetic activation contributing to our heart rate, our resting heart rate would be around 100 beats per minute. Well, that's too much. It's not efficient for the activity of a person at rest. But if we did the other extreme, if we took out all sympathetic activation and only did parasympathetic activation, the heart rate would be around 40 beats per minute, which is way too low. That's not enough perfusion to get to all of your tissues. So in reality, to get us our resting heart rate around 70 beats per minute, we have both divisions communicating to the heart at the same time. So it's these receptors, alpha and beta receptors or muscarinic receptors at the SA node, they're receiving both norepinephrine and acetylcholine at the same time, and they're kind of summing that response to give us a resting heart rate of somewhere in between, around 70 beats per minute. What's nice about that is you could go in either direction now. So when you go to sleep, usually heart rates go down, maybe in the 60s, even in the 50s, depending on how healthy your heart is. And that would be the result of less sympathetic activation and more parasympathetic activation, slowing it down, okay? Then you wake up, you're back at 70 beats per minute, and then you go for a run or you're exercising. So now you're gonna have less parasympathetic and more sympathetic to give your exercising your target heart rate, 112, 115, whatever that happens to be. And then when you're done resting, we'll go back to a little bit of parasympathetic and a little bit of sympathetic to keep you back at rest. It's the same way with your blood vessel diameter. So you don't want to have all of your blood vessels open all of the time. That's inefficient. We don't want them all the way closed and can only open because that would restrict too much blood flow. So our blood vessels are kind of somewhere in the middle, kind of hanging out in its autonomic tone, and they have the ability to constrict and they have the ability to dilate depending on the demand of the tissue. So if it's exercising muscle, it can dilate. If it's during exercise, we can shrink the blood vessels to digestive viscera, so not as much blood goes there, and we can open the blood vessels up at the muscle, so the blood goes there, and vice versa during parasympathetic activation. So that's the idea of autonomic tone, this background level between the two divisions that allow your body to respond as needed depending on the scenario. And you don't have to think about it. It's automatic. That's the A, autonomic division. All right, so that's it. That wraps up our discussion on parasympathetic and then the little comparison about dual innervation here at the end. So the last video is going to be covering autonomic reflexes and higher order functions. So I will see you next time. Bye.